Namaste and hello everyone. Welcome to this session. So, in this session we are going to solve some examples on the topics and the concepts we learned in lectures L6 to L10, right, of this course on experimental model analysis. The topics we studied in these lectures were model analysis of multi-degree of freedom and damped systems. Then we studied model analysis of multi-degree of freedom systems with proportional and non-proportional structural damping. And then we studied model analysis of multi-degree of freedom systems with proportional and non-proportional viscous damping. So, please watch these lectures to learn and understand the background theory and concepts of the examples we are going to solve in this session. Let us get started with the session today, and let us consider example number 1. So, today we are going to have first 6 examples and then 2 examples after that based on the MATLAB script, right. So, let us get started with example number 1. Right. So, in this example we are essentially going to find the natural frequency and mode shapes of a given 2 degree of freedom systems, right. So, let us do that. So, let me write the question first. Find natural frequencies and mode shapes of the 2 degree of freedom coupled pendulum system shown in the figure below, right. So, let me sketch the system now. The system is something like this. We have 2 pendulums like this. They are identical pendulums and they are connected or coupled through a spring, right. So, therefore, the maybe we can develop first the equation of motion by taking the general values of the masses and lengths, right. So, let this be m1, this be m2, right, and of course, we are going to take this as m1 is equal to m, m2 is equal to m, right, and let us say k is the stiffness of the spring, correct. So, so this system now has 2 degree of freedom because both the pendulums can have independent or different displacements, angular displacements. So, if the angular displacement of pendulum 1 is given, then during vibration we would not be able to determine based on that the angular displacement of pendulum 2. So, right. So, they are independent in that sense, and hence this system has 2 degree of freedom. Let us say 2 degree of freedom system. And what are the degrees of freedom? That if I consider the displacement of the pendulum, right, then this pendulum may displace like this, and then this pendulum may displace like this. So, this is theta 1 and this is theta 2. So, the 2 degrees of freedom are theta 1 and theta 2. Okay. So, 2 coordinates are required to specify the displaced configuration of this system. So, now to determine, so therefore, our step would be first we will write the governing equations of motion, right, and then we will solve those equations to find the natural frequency and mode shapes. So, let us do that now. Let us have solution. We would consider the pendulum to be displaced from the rest position, the mean position, which is the vertical position of the pendulum, which is the mean position, and then we will see, make the free body diagram of each pendulum, right, so that we can apply, let us say, Newton's law to the pendulum's motion. So let us consider the so let me sketch that free body diagram on this side. So let us make the free body diagram, right, and so this is a pendulum 1. So this is the mean position, and now this pendulum is displaced from here like this, right. Similarly, we have the pendulum 2, and this is the mean position, and let us say the pendulum is displaced like this. So this is theta 1 and this is theta 2, correct. So the forces, let us try to indicate the forces. So of course we will have the gravity force here, m1g acting here, and here you will have m2g, correct. And then the spring will suffer deflection, and the deflection of the spring will be equal to, if let us say in the this distance which of the spring, right, is a, where the spring is attached to the pendulum, the distance from the support is, let us say, a, and of course also assume that the length of the pendulum is L, something like this, right. And of course we can and then of course we can then here write down the force due to spring, how much that force would be. So let us say we have the deflection of the spring would be a into theta 2 minus theta 1, correct, and therefore the spring will apply a force on this pendulum in this direction, and it will apply a force on this pendulum in this direction, right. For example, if I assume that theta 2 is more than theta 1, then the spring would basically have a net extension, and when the net extension is there, it will try to basically apply the opposite forces at the two ends on the two pendulums, and that is how we have determined the angle or direction of these forces. So therefore this force would be k into theta 2 minus theta 1 into a, correct. So that is going to be the force on the spring. Of course here we are assuming the angle to be small. So now we can apply Newton's law to this. So let us do that, let us apply the Newton's law. So applying Newton's law to pendulum 1, right. So of course this is the pendulum 1, right, and this is pendulum 2. So therefore the moment about the point at which it is hinged to the support at the top, at that point the moments can be taken, and that should be equal to, if let us say the moment of inertia of the pendulum about that point is I, and if theta double dot, so let me also mark here, let us say the theta 1 double dot is the acceleration of the angular acceleration of this pendulum, and theta 2 double dot is the angular acceleration of this pendulum, then now we can write down I theta 1. So it maybe we can write I1 because we have taken mass m1. So I1 theta 1 double dot is equal to, then we have the k, right. So k theta 2 minus theta 1 into a, right, into a, because now we have to take the moment, correct, and then minus for small angles, now we can write this as m1 g theta 1, right. So actually this distance, for example the distance, this is the moment arm, right, for the, in the figure this is the moment arm for the m1g, and this quantity is actually equal to L sin theta 1, right. The distance of the m1g from the center line is actually, this distance is, we can write here as L1, L we have taken, so L sin theta 1, correct, and if angle is small, then sin theta 1 will be approximately equal to theta 1, and so that is what we have done, right. And then this is the equation for first pendulum, and then for second pendulum. So let us apply Newton's law to pendulum 2, we can write down I2 theta 2 double dot is equal to, now the spring force resists the acceleration of pendulum 2. So, we will have minus sign here, minus k theta 2 minus theta 1 into A, correct, and then we have here similarly we will have m1 m2g now, m2g, so that length would be, this length here is L sin theta 2, right. For small angle sin theta 2 will be approximately equal to theta 2, and hence we can write this as m2g theta 2 into L. Sorry, I forgot to write L here in this first equation, right. So, this is basically these are the two equations. So, now we can of course, let us further simplify this. So, now I can simplify this equation maybe here. So, here now I1 theta 1 dot is essentially m1 L square, moment of inertia of the mass of the pendulum 1, the bob of the mass of the pendulum 1 is m1. So, m1 into L square is the moment of inertia about the point of connection. So, m1 L square plus then we will have theta 1 into bracket k s square plus m1 g L, right, then plus theta 2 into bracket minus k a square is equal to 0, correct. Similarly, the second equation would give us m2 L square, sorry, I forgot to write here theta 1 double dot, right, and theta 2 double dot plus we will have theta 1 minus k s square plus theta 2 into bracket k s square plus m2 g L is equal to 0. So, these are nothing but the equations of motion. What are these? These two are the equations of motion, and because system is of 2 degree, right, and that is why 2 degree of freedom, and hence we have two simultaneous second order differential equations. So, when we had single degree of freedom system, we had one such second order differential equation. Now, because it is a 2 degree of freedom system, we have two simultaneous second order differential equations, right. So, they are simultaneous in the sense that they are dependent. So, we cannot solve these equations one by one, we cannot, we have to solve them together, because the coordinates are coupled. You can see theta 1 theta 2 they appear in both equations, correct. It is not that pendulum 1 is dependent, pendulum 1's equation is dependent only on theta 1, theta 2 is also there, and same thing is true with the equation for pendulum number 2, right. So, now we need to solve these equations, right, and and there is no forcing term on the right hand side. So, it represents basically the free vibration of the system, there is no forcing term here on the right hand side, you can see it is 0, correct. So, now let us go to next page. So, let us first write the equation in matrix form, right. So, if you write it in matrix form, maybe equations in matrix form, we can write it in compact matrix form. So, we can combine the theta 1 double dot and theta 2 double dot into a single vector, right, like this, theta 1 double dot and theta 2 double dot, correct, and then we can also combine the theta 1 and theta 2 into a vector like this. So, now it is easy to identify the coefficients of theta 1 dot and theta 2 dot in the first equation, and those coefficients are m1 L square and 0. Similarly, these coefficients of theta 1 dot and theta 2 dot in the second equation are 0 and m2 L square. In the same way, we can identify the coefficients of theta 1 theta 2 and write these elements of this matrix. K s square plus m2 gl. So, this essentially now you can see it is in the equation of motion in the matrix form, and then we can symbolically represent this equation as, we can call this coefficient matrix as mass matrix. This is the vector of accelerations theta double dot, plus this matrix is, we can call it stiffness matrix, and this is the vector of the angular displacements theta, right. So, this is mass matrix and this is stiffness matrix, correct. And now to solve this equation, now let us assume the solution as, so let we assume the solution as theta is equal to theta naught cos omega t. So, we are assuming a harmonic solution, correct. We are assuming a harmonic solution where the amplitudes of the displacements of the two pendulums, they are contained in the vector theta naught, right, and omega is the frequency of motion. And let us see whether this can satisfy the equation of motion. So, of course, we have gone through this process in the lecture classes where we evolved and got the eigenvalue problem, right, but I am just repeating those steps here to clarify the concept. So, if you substitute this in the equation of motion, then you get minus m omega square, and then your theta naught plus k theta naught cos omega t is equal to 0, right. So, obviously because omega the t, the time variable is arbitrary, cos omega t is not 0 for general t, right. For a general t, cos omega t is not 0, right. So, therefore, this quantity must be 0. So, therefore, I can write this as minus m, I am sorry, I think it should be theta naught m minus omega square theta naught, right. So, this quantity then obviously should be 0, right. So, let us further write on this side. So, we can therefore say that k theta naught is equal to, if I call this quantity as lambda omega square, then I have m theta naught, correct. So, this is nothing but the eigenvalue problem. This is eigenvalue problem. Therefore, to solve this problem, the determinant of the coefficient matrix must be 0. So, determinant of the coefficient matrix must be 0, correct. So, for that to happen, we need to take the determinant of this matrix, which is k minus lambda m, right, this matrix must be equal to 0. So, what this matrix would be? It would be k s square plus m1 g l minus maybe I can write here lambda, right, that is m1 l square, okay, minus k s square minus k s square and then k s square plus m2 g l, right, minus m2 l square lambda. So, this determinant should be equal to 0, okay. And just now to solve this further, let us assume now we take m1 m2 same. So, let us solve this eigenvalue problem for this special case where m1 and m2 are same, right. And then if you do the multiplication and all this, then what do you get? K s square plus m g l minus lambda m L square, right, and the square of this minus a square square of this. So therefore I have a square plus mgl minus lambda ml square. So it is a square minus b square. So I can write it as a plus b and a minus b, right, like this. Okay, multiplied by mgl minus lambda ml square is equal to 0, correct. So therefore the first root would be here. What that root would be? It would be lambda 1, correct, and that lambda 1 would be actually equal to g by the first root would be lambda, that will be g by L, right, and the second root would be g by L plus 2 k s square upon m L square, correct. So therefore the natural frequencies would be square root of this. So let us go to next page. So therefore the natural frequencies are omega, maybe I can call as omega 1, and that will be equal to the square root of lambda 1, and this would be equal to the square root of g by L, and then I have omega 2, that will be square root of lambda 2, and that would be square root of g by L plus 2 k s square upon m L square. So in this way we got the two natural frequencies. And now so therefore we will also have no corresponding eigenvectors corresponding to the eigenvalues, right. So the lambdas are the eigenvalues, and square root of these eigenvalues we got the natural frequencies. So for these two eigenvalues there would be corresponding eigenvectors. So let us determine now the eigenvectors. Now let us find eigenvectors. So to find eigenvectors, what we do is that we substitute the eigenvalue, right, in the the equation we got. So what equation we had? Let me write that equation, the eigenvalue equation, that was k s square plus mgl, right, and then we had minus lambda 1, right, that was the first eigenvalue, minus k s square minus k s square, and then we had k s square plus mgl minus lambda 1, right, and lambda 1 of course into ml square. I forgot to write ml square, correct, and then we had the displacement vector here. Let us call that as theta 10 and theta 20, right, and this will be equal to 0. So what we have done, we have substituted in place of lambda 1, correct. So this has been obtained by substitute lambda is equal to lambda 1, because we are interested to find a corresponding eigenvector. And now we solve for this vector theta. So if you do that, then if you multiply these two equations, multiply the matrix and the vector, what you get is basically k s square. From the first equation we get I think, let me just we should remember that these are the matrix elements like this, right. So now here lambda 1 is g by L. So this would essentially cancel with this when you substitute lambda 1 is equal to g by L, right, and then you are left with the matrix k s square minus k s square minus k s square and k s square, correct. So because here also this also would basically cancel, right, and then we get theta 10, theta 20, 0, 0, correct. So essentially what we have got, k s square theta 10 minus k s square theta 20 is equal to 0, right. So which means that if you can see the second equation is also same as this, correct. So, essentially we only have one equation and there are two unknowns, theta 10 and theta 20. So, they cannot be determined in a unique way, correct. So, we will have to assume one of the unknowns, right, and then find the remaining unknown. So, if I assume, let us say let theta 10 is equal to 1, then solving this I get theta 20 also as 1, correct. So, other way to state this is that I can solve this equation for only the ratio. I can say that theta 20 upon theta 10 is equal to 1. So, this is the solution only I am able to get, correct. So, I can assume assign any value to theta 10 and I would get the corresponding value of for theta 20 from this ratio. So, therefore, this is the basically what we get as the eigenvector. So, if I now write here, so therefore, theta 10 theta 20 I can write as 1 1, and this is nothing but the eigenvector for the eigenvalue lambda 1, right, and this is also called mode shape, and because here one of the variables are assigned arbitrary value. So, the scaling of this vector is arbitrary, it has arbitrary scaling, correct, which means that we can change the multiply this vector by any constant, any scalar. The eigenvector as such will not change, but the overall scaling will change, right. So, this is the first mode, and then if you sketch this mode, how it appears. If you sketch this eigenvector, then this is the mean position of the pendulums, right, and then when it vibrate in the first mode in this with this eigenvalue and eigenvector, then if it is moving in this direction by some amount, then the second pendulum also moves by the same amount in the same direction, right. So, if it is moving by angle theta, then this also moves by angle theta. So, this is the vibration of the system in mode 1, right, and mode 1 is associated with the characterized by eigenvalue, natural frequency omega 1 and mode shape psi 1. So, maybe we can call this as psi 1, correct. So, they will keep on oscillating like this, but they would remain in phase and their amplitude of motion is same all the time. So, now the second eigenvector also we can easily determine in this manner. So, second eigenvector, so we need to substitute lambda is equal to lambda 2, right, and if you do that, the matrix you get is basically this minus k square minus k square minus k square minus k square, okay. So, theta 10 and theta 20. So, therefore, if you solve this, what ratio you get? Theta 20 upon theta 10 is equal to minus 1, correct, and therefore, now if you assume say if you take the assume theta 10 let us say arbitrary as 1, then we get the second eigenvector as theta 10, theta 20, 1 and minus 1, correct, that is the second eigenvector. So, therefore, in this mode what is going to happen? The pendulums are going to oscillate out of phase. So, the first pendulum if it has displacement theta, the other pendulum at that instant will have displacement minus theta, right. So, if sketch it here. So, what is going to happen if this pendulum is moving in this direction like this. So, this pendulum move in the opposite direction. So, if this is minus theta, this is theta, correct, and they would keep on oscillating. So, this means that in the first mode of vibration, the two pendulums, they are going to oscillate like this. They are going to oscillate in phase and with equal amplitude. But if it is oscillating in a second mode of vibration, the two pendulums will have opposite motion like this. They go their amplitude would be equal, but then they will be out of phase. Their motion will always be negative of each other like this. They are going to vibrate like this, the pendulums, right. So, therefore, this is the vibration in mode 2. Okay. So, I think in this way we have now solved this problem, and as we have found the natural frequency and mode shifts. Let us go to now the next problem. The next problem we are going to have is example 2, right. So, in this problem we are going the problem is something like this. Let me write it down formally. Question: find natural modes of vibration of a car based on the quarter car model, right, based on the quarter car model. And and what are the quantities which are given? So, the parameters are the system parameters are let me write here, the mass of the car body has been given as 240 into 4 kg, right. Mass of the wheel, one wheel is 36 kg. Then stiffness of the suspension, one suspension is 16,000 Newton per meter. Stiffness of the tires is given as 160,000 Newton meter, right, and the damping coefficient of the suspension is given as 980 Newton second per meter, correct. So, let me also just quickly make a simple sketch of the car body. Okay. So, there we are. So, this is the simple like sketch of the car body, and then what is quarter model, quarter car model. So, quarter car model essentially is based on the one wheel and suspension, right, supporting 1/4 weight of the car, 1/4 weight of the car body, which is above the suspension, right. So, that is basically called as quarter car model. Okay. So, we consider one so, we have the body of the car being represented by a lump mass mb, right, and that is 1/4. So, this is actually it is MB by 4. So, maybe I will make a small adjustment here. Let me call this this MB is in fact as MB dash, just to differentiate it from MB, right. So, MB is basically 1/4 upon MB dash. So, that is 240 kg, and then we have the suspension here like this, and suspension damping, suspension stiffness and suspension damping. So, this is Ks and Cs, right, and then we have the wheel mass again shown by the one lump mass of value mw, and then the stiffness of the tire, right, that is being shown by a lump stiffness Kw, correct, and then of course this is the uneven road profile, right. So, this is essentially the quarter car model. What this is called quarter car model. So, let us solve this problem. So, this quarter car model generally is used for studying the ride comfort analysis. Okay. For studying the ride comfort, this model is used. If I just abbreviate it as QCM. So, QCM is used to study ride comfort of the vehicle. So, with this model we are trying to study that if let us say car is moving on a rough road, then what is the vertical acceleration of the car body, that is what determines the ride comfort, right. So, study the vertical acceleration of the car body. Why? Because car body carries the passenger seats, right. So, if the car body vibrates significantly and has significant vertical acceleration, the passengers also will be basically subjected to that acceleration, right. So, that is why we wish to study what is the vertical acceleration experienced by the car body due to movement over the road, irregular road, so which causes the base excitation, and then there would be forces due to the whole machinery of the car, right, engine, powertrain, all this gearbox, everything will basically generate some forces which will also excite the car body. So, due to base excitation from the irregular road and engine, powertrain and other excitation forces, correct. So, that is what we wish to study using this model. So, therefore, in this particular problem we have been asked to find the natural modes of vibration of this, correct. So, so let us go to next page now. And let us now write the equations of motion. So, now again if you consider the mass, the vertical motion of the body of the car represented by xb, right, and then if we represent the motion of the wheel mw by xw, right. So, let us now represent what are the forces which are going to act, and of course, here we are because our interest lies in studying essentially the natural modes of vibration. So, here we are going to solve the undamped model of this of this car system, right, undamped model. So, we will ignore the defect of damping, right. So, let us focus solve the undamped model to find natural modes. So, essentially damping is ignored. Okay. So, what are the forces? So, obviously this you will have the force on the car body, which will be equal to Ks into xb minus xw, and same force also would act on the wheel, and then wheel also would be then subjected to force due to the coming from the stiffness of the tire, and that would be equal to Kw into xw, right. And therefore, now if you write the equations, what you would have, mb xb double dot is equal to minus Ks xb minus xw, and mw xw double dot is equal to Ks into xb minus xw, right. Okay, and minus Kw into xw. So, if you again simplify the way we did in the first problem, we will have this matrix equation xb double dot xw double dot is plus Ks minus Ks minus Ks plus Aw, right, and xb xw is equal to 0, correct. So, therefore, now if you use the parameters which are given to us, then essentially we have got the mass matrix, which is this matrix. This is the stiffness matrix, correct. This is the x double dot vector, and this is the x vector. So, the mass matrix is 1/4 of the body mass, 1/4 mb dash upon 4, that is 240, and then we have this is 36, and then we have the stiffness matrix, which is 16,000 minus 16,000, and then we have 176,000, correct, that is K. So, now here we can therefore solve for the eigenvalues and eigenvectors, correct. So, you have the determinant of K minus lambda m is equal to 0. When we solve this, solve the eigenvalue problem. When you solve this eigenvalue problem, you get eigenvalues and eigenvectors, and then we can find the natural frequency and mode shifts, right, by taking the square root of the eigenvalues and then substituting the eigenvalue in the parent equation and then solving for the eigenvector. So, I will now directly write the results, you can just proceed this. So, what are the natural frequencies now? Natural frequencies are this we can call as omega 1, and that comes to be 7.78 radians per second, okay. And in terms of hertz, this is 1.23 hertz, correct. And the second natural frequency is omega 2, and that comes to be 69.96 radians per second, and in terms of hertz it is 11.13 hertz. And then if you look at the mode shapes, that is nothing but eigenvectors, right. Those mode shapes, and if you mass normalize them, so I also in fact mass normalize them, mass normalized eigenvectors, right, means you basically, we studied in the lecture classes that when we take phi transpose, whatever eigenvectors we got, if you call it as psi transpose m psi, that basically gives you the model masses, and then you divide each eigenvector by the square root of the corresponding model mass, then you get the mass normalized eigenvector. So, if you do that mass normalized eigenvector, if you represent it by that is what the convention we have been using, phi, that is the mass normalized eigenvector, and psi is the which is not mass normalized or with arbitrary scaling. So, that is psi. So, this is what we are calling it as phi. So, phi 1, this is found to be 0.064 and 0.0059, right. this eigenvector, and then second eigenvector we got as minus 0.0023 and 0.166, right. So, let me just box this, all this easier to view then, right, something like this. So, now let us look at the results. It is pretty interesting. If you look at the mode 1, so this is mode 1, maybe I can write that here. This is mode number. So, this is first mode, this is second mode. Right. So, this is the first mode. The first mode natural frequency is 1.23 hertz, very low frequency, right. So, actually this is called essentially and then also if you look at the eigenvector, then the first element is 0.064. So, this represents essentially the amplitude of the if you look at this one, this represents the amplitude of the body, right. It represents the amplitude of the body, means it represents xb, this represents amplitude of the wheel when this system vibrates in this mode. Then and of course, this is the scaled amplitude, it is not the absolute value of the amplitude, but in relative sense if you look at, then what do you see from here, that in the first mode of vibration of this car body, of the car system, I mean, the amplitude of the body is much larger than the amplitude of the vibration of the wheels, correct, and that is why this particular mode is called sprung mass mode. Okay. So, this particular mode is called as sprung mass mode. Correct. And if you try to plot this, let us say this is the mean line, and if I represent the displacement in the horizontal direction, although the actual displacement are in the vertical direction, but in order to plot and visualize that, let us plot that in the horizontal direction. So, the first mass which is here, say the wheel is here, right, then this mass is going to have significant movement, but this mass is having smaller movement, right, almost 10 times less, something like this, but they are in phase. So, they move in the same direction. So, it means that if I now join this point like this, correct. So, this is the motion of the system, and this of course is the ground, this is the ground here. So, it means this mass is going to move significantly, the body is going to have a significant motion in the sprung mass mode, but the wheel they do not move so much, correct, they do not move so much. Similarly, if you look at the second mode, the natural frequency of that mode is 11.13 hertz, which is much larger than say the first mode, right. But if you look at the mode shapes now, the first mass has a much relatively smaller displacement in this mode, that is the body has a much smaller displacement in this mode as compared to the wheel displacement, because the wheel displacement is 0.166 while the the body displacement is just 0.0023. So, therefore, if this also we try to sketch like this, and if this is the body mass, this is the wheel mass, then now here the wheel is going to have a significant displacement like this, okay, and also the motions are out of phase. So, if the wheel is moving up, then the body is moving down, right. So, therefore, this is going to move here at this time. It means that if I at this instant, this is the basically mode shape or the deflection shape, and on the other side this shape is like this, like this. So, motions are out of shape. So, this is called unsprung mass mode. Correct. So, in fact, the body is referred as the sprung mass. This body MB, it is referred as the sprung mass, because it is above the suspension, right, and therefore therefore it is called sprung mass. And the wheel when it is having significant motion, that is referred as unsprung mass. So this we can refer as unsprung mass, because it is below the suspension, it is not above the suspension. That is how you can remember it, right. So I think this basically interesting results we have got, right, sprung mass mode and unsprung mass mode. And these modes you can see they have 1.23 hertz and 11.13 hertz. So in fact the ride comfort of passengers, it is determined by the vibration in the range from 0 to 25 hertz. The ride comfort is determined in this range 0 to 25 hertz, because most of the our body organs, their natural frequency is very small, something like 1 hertz, 2 hertz, 3 hertz, 4 hertz, it is in that range, small range. And that is why these modes play a significant role, because they are in this range where the body resonances lie, and they and the vibration in those frequencies may make us uncomfortable, the passengers uncomfortable, right. So that is why these modes are important when we design the suspension, right. Let us go to the next problem now, problem example number 3. Right. So let me write the question first. So find free vibration response of the 2 degree of freedom system in the figure below to different initial conditions which are, so the first part is the initial conditions are we have the vector x, that is the displacement vector s at t is equal to 0 x naught, that is given as 2 0, and the initial velocity vector is all zeros, right. Then we have the b where x naught is now 2 2 and v naught is again 0, and then we have the part C, we have 2 minus 2 and v naught is equal to 0 0, right. And what is the system? The system is this system we also studied in the lecture classes, right. To study the eigenvalue problem we have considered this system is the 2 degree of freedom system, where x1 and x2 are the 2 degrees of freedom, and both are equal masses and the spring stiffnesses are also equal, correct. Right, and the values are m is equal to 2 kg and k is equal to 1000 Newton meter, right. So let us solve this problem. Let us solve this problem. So definitely we can now easily again solve the eigenvalue problem and find the natural frequencies and mode shapes, and let us say the those are identified already. So solve the eigenvalue problem, right, which gives us the natural frequencies. So that I am going to directly write here, that comes as 22.3 radians per second, and the mode shape, it is the arbitrarily scaled mode shape, that is 1 and 1. So, this in fact we have solved in the lecture classes. Only thing is that now we have substituted the values of m and k in those expressions and we have got the eigenvalues. So, and then the second mode has natural frequency 38.7 radian per second and the mode shape is 1 minus 1, correct. So, now what is the general solution? The general free vibration solution, general free vibration solution, what that would be? It would basically consist of the linear combination of free vibration solution in all the modes, right. In each mode whatever is the solution you have to linearly combine them and then get it. So, as we saw in the lecture classes, we can write the general free vibration solution X as sum of the solution in the each mode psi I psi I cos omega I t, right, plus b I psi I sin omega I t, with I varying from, in this case there are 2 degrees of freedom, there are 2 modes. So, it varies from I is equal to 1 to 2. So, here A I and B I are the arbitrary constants. What are A I and B I? A I and B I are arbitrary constants. Correct, and they depend on initial conditions and they depend on their values depend on initial condition. What are the initial conditions? Correct. So, let us now take the initial conditions and solve for A I and B I, correct. So, let us go to next page. So, if I assume the initial conditions as let at t is equal to 0 x naught, if I call it x1 naught and x2 naught, and the velocity is 0 because in the parts A, B, say A, B and C, the velocity, initial velocity is anyway 0. So, we just let us take the general values of the displacement, and after we get general expressions, then we can substitute the actual values of the initial displacement to get the corresponding free vibration response, right. So, let us do that. So, if you substitute this initial condition in the expression for the free vibration response, then what do you get? X naught will be equal to I is equal to 1 to 2 and then A I psi I cos omega I t, t is 0, right, plus B I psi I sin omega I t 0, right. So, this essentially becomes A I psi I with I varying from 1 to 2. So, this is the equation we get, right, because cos 0 is 1 and sin 0 is 0, right. Now, let us apply this condition to the velocity. So, the velocity, then first of all we will have to differentiate the expression for x of t. If you differentiate that, then you essentially get velocity x dot, and that would be equal to again sum from I is equal to 1 to 2, correct, and then you have cos is differentiated as sine. So, you have minus A I psi I omega I sin omega I t plus B I psi I, then you will have omega I cos omega I t, correct. Differentiation of sin omega I t is cos omega plus cos omega I t. And now if you apply the initial conditions at t is equal to 0, then this is 0, correct, and then we get I is equal to 1 to 2, right, and when t is equal to 0, the first term would be 0, and then we get bi psi I omega I, sorry, it is omega I not psi I, omega I like this, correct, that is what we get. Okay. So, therefore, this is the second expression we got. So, we can now solve this equation. For example, if you look at this one, we could have easily worked out if you now substitute the psi and x naught here, what you would get essentially would be you would have a1 x naught 1 will be equal to a1 plus a2 and x naught 2 is equal to a1 minus a2, and if you solve for a1 and a2, and what you get essentially is a1 is equal to x naught 1 plus x naught 2 upon 2, right, and a2 is equal to x naught 1 minus x naught 2 upon 2. So, these two general expressions you got for a1 and a2, and similarly if you look at this equation for the velocity, then here you would see that because if you substitute this thing, what you are going to get is omega 1 omega 2, right, omega 1 minus omega 2, and then you have b1 b2 is equal to 0 0, correct. So, these are basically the homogeneous equations, these are homogeneous equations, and what we see that the coefficient matrix is basically has full rank, correct, its determinant is not 0, which means that these two equations are independent, they are not dependent, right, and hence the only solution in this case for vector b is that vector b should be 0. Therefore, the solution would be that b is equal to 0, which means that b1 is equal to 0 and b2 is equal to 0. So, you can see these are the results we got, right, and that is why now we can easily write the we can obtain now the use these results to obtain the free vibration response for the 3 cases. So, let us do that now. Let us take the case A. In case A, we have got x naught 1 is equal to 2 and x naught 2 is equal to 0, that is what is given to us, correct. So, if you substitute these results here, what are you going to get? You are going to get A1 as 1 and A2 also as 1, right, and of course, B1 is anyway 0, B2 is also already 0. So, what is the free vibration response? Therefore, the free vibration response would be x1 t, x2 t. So, A1 is 1 and then the eigenvector psi 1, that is 1 1 and then cos omega 1 t, correct, plus A2 which is 1 and then you have the second eigenvector 1 minus 1 and cos omega 2. Sign terms are anyway 0 because coefficients b1 and b2 are 0. So, here what we see that the x1 t now can be written as 1 cos, we are given as 22, right, as the first natural frequency, plus 1 cos 38 t and x2 t is equal to 1 cos 22 t minus 1 cos 38 t. So, these are the free vibration responses when the initial condition is like first mass being displaced by 2 units and second mass being displaced by 0 units, no displacement. So, what we see that the vibration response of the two masses, they contain now presence of both the modes of vibration, because we can see from the equations that not only the first initial frequency 22 radian per second, but also the second one with 38 radian per second is present in the response. So, it means both the modes are excited with this kind of excitation, right. The kind of initial excitation conditions given, both modes are excited, and that is why if you measure the vibration response of each mass, for example like this, say x1, x2, I am just roughly qualitatively sketching what is likely to be seen. This may look like this. It is non-harmonic, both the frequencies are present, both the natural frequencies are present in the response. We do not see the response as harmonic, right. So, therefore, this is what we are going to see, and if you take a frequency spectrum of this, you would see the two peaks, you will see the peaks at the both natural frequencies. So, if you see the if you take the the spectrum of the signal, what is going to happen. If you see the x1 omega, then you are likely to see, you are going to basically see one peak at omega n1, and then you will see another peak at omega n2 like this. In both, for x2 also same thing would be true. Is that okay? So, now let us take the second case B. So, if you take the case B, then for case B, what are the values of x01 and x02? It is 2 and x02 is also 2. So, if you solve for A1 and A2, then you get A1 as 2 and A2 as 0, because A2 was x1 x01 minus x02 upon 2. So, this means that now if I write the free vibration response, right, then I have x1t, x2t, right. So, A1 is 2, correct, and then we have the first eigenvector which is 1 1, and then you have cos 22t, right, and then A2 is 0, and of course B1 B2 are anyway 0. So, therefore, essentially what we are having is x1t is simply now 2 cos 22t, and x2t is just also 2 cos 22t. So, look at this. Now, you can see the vibration response of x1t and x2t consist of only one natural frequency, 22 radian per second. The second natural frequency is not excited, the second mode is not excited, right, and hence it does not contribute anything to the response. And therefore, if you sketch this response, then in the time domain the response may would look something like this. It is a cosine wave, pure cosine wave, right, and for x2 also the same, exactly same wave, because it has the same amplitude, correct. And also you see the absolute values of amplitudes, they are like 2 2, but if you see the ratio, right, if you normalize these values to say with x1 amplitude normalized to 1, then the amplitudes basically would be same as the eigenvector, first eigenvector, which is 1 1, correct. So, the absolute displacements, their values may be different, but their ratios, they exactly comply with the corresponding eigenvector, right. So, the first mode shape completely determines the displacement shape, right, of the vibration profile or the pattern of the whole system, because in this case it is vibrating purely in the first mode. Now, if you look at the next case now, so of course, to complete the story, let me also say that if you now take the Fourier spectrum of this, you take the Fourier transform of this and plot that on a frequency domain, then basically now you are going to see only one peak in the response, right. You are going to see only the one peak in the response in the frequency domain, because there is only one natural frequency which is basically contributing to the response. So, let us now take the last case, which is case C, and in case C we had x naught 1 was equal to 2, x naught 2 was equal to minus 2, and if you solve for A1 A2 you get A1 as 0 and A2 as 2, right. And then if you again go through this whole process and write down the response for the two masses, then A1 is 0, so 0, and then A2 is 2, and the second eigenvector is 1 minus 1, and the frequency is 38t. So, which means that x1t is actually equal to 2 cos 38t, and x2t is equal to minus 2 cos 38t, right. So, what we see, only the second eigenvector is second mode is present, right, only second mode is present. So, only mode 2 is excited, correct. So, of course, here also same thing we can say, here only mode 1 is excited, right. So, here therefore, what is going to happen, if you now see the response, again it will be a cosine wave at higher frequency x1, and x2 would have the same frequency, but it is out of phase. So, therefore, x2 will basically have this kind of cosine wave, right. And that is why if you now see the Fourier spectrum, then you are going to see now the mode this thing at this is at omega, right, this is at 38, you will see the peak, and here also you would see the peak at this. I am showing the magnitude plot. So, here the phase is not visible. If you show the phase also of the spectrum, there you would see the difference in the phase, right. So, here this is 22, okay. So, therefore, now what is the conclusion? The conclusion is that depending upon what kind of initial disturbance is given, that would determine the kind of modes that are excited. If you give a very general disturbance, right, then most likely all modes would be excited, correct. Of course, then it also depends upon what are the different nodes of the modes and what displacements are given at different degrees of freedom. So, in general what will happen, a general arbitrary excitation would in general lead to excitation of all the modes, and if you take the Fourier spectrum of the time domain response, in such a case then you are likely to see the peaks at all the natural frequencies. But if you want to excite a specific mode, then what kind of initial disturbance needs to be given? That initial disturbance, let us say initial displacement, by holding velocities to be 0, by the initial displacement of the different degrees of freedom must comply with the mode shape of the mode which needs to be excited. So, if I wish to excite mode number 1, then the initial displacement at different degrees of freedom must comply to the mode shape of first mode. Then what is going to happen? Only the first mode will show its presence in the response, right. And if you therefore take the Fourier spectrum, you would see only the peak at the first natural frequency, right. So, let us now go to the next example. So, example number 4. So, let me write the question first. So, this question is about model analysis of system with the force vibration. The previous problem was about the looking at the free vibration response and seeing that what different modes are excited. In this case, we are going to look at the model analysis of the multi-disruption system under force vibration. If harmonic forces of amplitudes minus phi Newton and phi Newton and frequency 24 radians per second act on the two masses for the system given below. Determine the modal forces and steady state modal and physical responses. So, the system given is the mass matrix is given as 2002, the stiffness matrix is given as 2000 Newton meter minus 1000 minus 1000 and 2000, correct, and natural frequencies are also given. The first natural frequency is 22.3 radians per second, and corresponding unscaled mode shape is given as 1 and natural frequency is second frequency is 38.7 radian per second, and the corresponding mode shape is given as 1 minus 1, right. And the force vector amplitude which is given in the text of the problem, that is nothing but we can write that as minus phi and plus phi, and the excitation frequency omega is 24 radians per second. So, this is the basically the problem. Let us solve this. So, here we have to find the modal forces and then the modal responses also, from which then we will find the physical responses. So, to find modal forces and also to physical modal responses, it is best to first convert the unscaled mode shapes into mass normalized mode shapes. So, to do that, first we should find out what are the modal masses. So, let us find first of all the modal masses. Okay, we find the modal masses, right. To find modal masses, what are modal masses? The modal mass matrix is given by, is written as diagonal MR matrix, and that is equal to we first we need to take the transpose of psi matrix, mass matrix and psi matrix, correct. And what is psi basically? Psi is the eigenvector matrix. This eigenvector matrix is in the present case, the eigenvector matrix as a standard convention contains the columns as the eigenvectors. That should always be remembered, right. It is the column which is the eigenvector, not the row. So, the first column is the psi 1, this is the first eigenvector, and the second eigenvector, second column is the second eigenvector psi 2, right. So, if you therefore combine this, you get 1 1 and 1 minus 1. So, that becomes the eigenvector matrix. So, now if you substitute this here, then we can then obtain the substitute psi and m here, right, and then multiply. If you do that, you get 4004. So, you need to multiply the 3 matrices, which is easy in this case, it is a 2 degree of freedom problem, right. So, we get this result. So, therefore, these diagonal entries are nothing but the modal masses. So, therefore, MR1 is 4 and MR2 is also 4. These are nothing but the modal masses for the two modes. So, MR1 is the modal mass for mode 1 and MR2 is the modal mass for mode 2. So, one should remember that when we say MR1, MR2, they do not represent lump masses, they represent effective mass of the system if the system is vibrating in the first mode. Mr2 represents the effective mass of the system if system is vibrating in the second mode. So, it represents the effective mass of the whole system, not of any particular mass, of any particular lump mass. So, now we find the mass normalized eigenvectors, correct. So, how to find mass normalized eigenvectors? Mass normalized eigenvectors. So, we represent the mass normalized eigenvector by symbol phi. So, phi 1 will be equal to, you divide the unscaled eigenvector by the square root of the corresponding modal mass, right. So, if you do that, this would be 1 divided by square root of 4, that is 2. So, this becomes 0.5, 0.5. So, this is the mass normalized eigenvector 1. Similarly, the mass normalized eigenvector 2 would be equal to psi 2 divided by Mr2, which means 1 minus 1, 2, and that would be nothing but 0.5 and minus 0.5. So, in this way you can see we have obtained the mass normalized eigenvectors from the modal masses, correct. And now next thing, now we can obtain the modal forces. Let us go to next page. So, now we can find modal forces, right. And we have learnt in the lecture classes that the vector of modal forces, the amplitude of the modal forces is nothing but equal to the mass normalized eigenvector phi transpose and the multiplied by the physical force vector, correct. So, this is the case. So, therefore, this is we can call as Fr1, Fr2, and now 1, 1, 1 minus 1, right, that is the phi transpose, and multiplied by the physical force vector, that is minus phi plus phi, correct. So, if you do this multiplication, matrix vector multiplication, you essentially get Fr1, Fr2 as 0 and minus phi. That is very interesting result, right. So, what we have got? We have Fr1, which is the modal force for mode 1, that has turned out to be 0, right, and Fr2 is the modal force for mode 2, and that is minus phi, right. What does this mean? Because the modal force basically represents the effective force vector, which is, or effective force which is exciting the mode, particular mode, correct. So, physical forces F naught minus phi, they are the absolute or actual forces which are acting at different degrees of freedom. But modal force, for example Fr1, it represents that how much of that physical force vector is exciting mode 1, right. And in this case we got that as 0, which means that the force vector that has been applied on the system is not exciting the mode 1 at all, it is not exciting at all, and hence obviously no modal response in the first mode would be created. So, that is a very important insight we have got, and Fr2 is the modal force which is non-zero in this case, and that is being excited by the applied force vector, correct. So, the force vector that has been applied is such that it is not exciting the first mode at all, it is exciting only the second mode. So, the next thing is, now we need to find the modal responses, correct. Let us find the modal responses. Right. So, we studied in the lecture classes that the amplitude of the modal response YR, right, YR naught means for the rth mode what is the response is Fr naught divided by omega r square minus omega square. So, it means if I say what is the modal response in mode 1, modal response in mode 1, if that I want to know, then what is the equation? Then I have y1 naught, right, is equal to f, maybe in the notation I have used on the left hand side I can say FR1, right, or divided by omega 1 square minus omega square. So, actually this FR1 actually is in the on the left hand side. If I just rewrite this, this I can write as F10, F20, which are the model responses 0 and -5 like this. So therefore, if I go by this, then I can actually also write this as F10 upon omega 1 square minus omega square, just little conflict of notation. So therefore, now if I substitute this here, of course F1 is 0, so clearly Fy10 is 0. So the modal response of first mode is 0, right. Now modal response of mode 2, right, modal response in mode 2 would be Y20, it will be equal to F20 upon omega 2 square minus omega square, correct, and omega is already given to us, excitation frequency is given to us. So if you substitute this, so you have -5 divided by 38.7 square minus 24 square, and you get minus 0.0054. So that is nothing but the modal response in mode 2. So that represents, again, it is not the value of the response at any particular degrees of freedom, right, it is the modal response. So it says that this is the amount by which the second mode is excited. But now if you wish to know the actual value of physical displacement at different degrees of freedom, then we will have to find the physical response, which is what we are going to do next. So let us do that. Let us find physical response. Right. So the physical response is as we studied in the lecture classes, the physical response is related to the modal response by modal transformation, like this, correct. So it means that x1, x2, correct, and these again are the basically the amplitudes of the responses, and this is now 1, 1, 1, -1, correct, into y10, y20. So this is a general like so therefore what we have got, we have 1, 1, y10 plus 1 minus 1 y20. So from this equation it is very easy to see that y10 and y20, what do they constitute? They essentially constitute the amplitudes of the response in different modes. That is why they are called as modal responses, right. And obviously now if you substitute our results, the first one is anyway 0, and then you get the result as plus, right. If you substitute this thing here, I am sorry, I think this is actually 0.5, not so maybe I can divide the whole thing by half, divided by 2, right. So this is half. So the 1, 1, 1 minus 1 were the unscaled ones, when then we mass normalize them. So each one got divided by, each vector got divided by 2, right. So therefore the result would be minus 0.0027 and 0.0027. So these are the physical values of the responses. So at first degree of freedom, the amplitude of displacement is minus 0.0027. And then of course there is cos omega t, which describes the time domain response, same form as that of the forcing function, and in the second degree of freedom the displacement is 0.0027. So this completes our solution of example number 4. Let us go to next example. Example 5. Right. So the question is, the mass matrix M stiffness matrix K and mass normalized eigenvectors phi of a 2 degree of freedom system are given below. Okay. The system has proportional viscous damping such that the damping matrix C is given as 0.0005 into the stiffness matrix. So, damping matrix is proportional to the stiffness matrix, that is what is given. And what we have been asked to do is to find modal viscous damping factors for the two modes. Okay. So, and what are the M and K are given? The mass matrix is 4001 and the stiffness matrix is given as 12 0000 and then you have minus 30 right, and we have also been given the mass normalized eigenvectors as 0.47, 0.28, 0.14, 0.95, right. What are these? These are the mass normalized eigen vectors, correct. So, let us solve this problem. Okay. So, of course, the damping matrix here is we can easily find out from the stiffness matrix. So, 0.005 into K and that comes to 60 minus 15 and 37.5, that is what we get as the stiffness as the damping matrix. Now, we have to find the modal viscous damping factor. So, from the given information what can we do is that because damping is proportional, right. So, we have studied in the lecture classes we can use a modal route to find the viscous damping factor. Let us see how we can do that, right. So, maybe I think I would go to the next page and then let us write down for free vibration. The equation of motion we know that it is given by mx double dot plus cx dot plus kx is equal to 0. So, instead of directly using some result to find modal damping factor, I am showing you that how fundamentally we can get to those relationships, right, which of course we have studied in the lecture classes to some extent, but just I am starting from a fundamental basis. So, this is the free equation of motion for free vibration of a multi-degree of freedom system. Now, let us consider modal transformation. Let us do modal transformation, which means that let us write x as mass noise eigenvectors and the modal responses, right. So, these are the x, they are the physical coordinates or degrees of freedom and these are the modal coordinates. So, basically we have transformed the physical system, we want to transform the physical system to the modal space, right. So, then what is going to happen, we can substitute x, we can replace x by this phi y, and also do pre-multiplication, also pre-multiply by phi transpose. Let us also pre-multiply by phi transpose. If you do that, then what equation you get? You get phi transpose m phi y double dot plus phi transpose c phi y dot plus phi transpose k phi y is equal to 0. That is what we get. And then we also studied in the lecture classes orthogonality properties of the eigenvectors, and from those orthogonality properties what we know, that from the orthogonality properties this quantity is phi transpose k phi, from the orthogonality properties is a diagonal matrix of the eigenvalues. So, this will be basically omega r square, a diagonal matrix of omega r square. Phi transpose m phi will be a unity matrix, because phi is nothing but a matrix of mass normalized eigenvectors. So, phi transpose m phi will be a unity matrix, which means that modal mass in each mode will be unity. That is what the property of a mass normalized eigenvector, the modal mass is unity. And now this matrix will be now a diagonal matrix, because in this case C is given as a proportional damping, right, and when proportional damping is there, proportional to stiffness matrix, mass matrix, or a combination, in either case the mass normalized eigenvectors, which are basically the in this case they are given as the mass normalized eigenvectors of an undamped model, they would be able to decouple the damping matrix, and that is why phi transpose C phi will also be a diagonal matrix, and that let us represent that we can write in the form of as 2 zeta r omega r. We can write it like this in the form of 2 zeta r omega r, right. So, therefore, this would be the basically the damping the diagonalized damping matrix. Okay. So, then what next? So, now these equations would be now they are all decoupled equations. So, above are all decoupled equations. So, then I can focus my attention on any one equation, they are all decoupled. So, each one can be treated independently. So, if you look at the rth equation, right, then what happens, I will have y r double dot, right, plus 2 zeta r omega r y dot plus omega r square y r is equal to 0, correct. And let me now use this space, right. So, therefore, from here what do you get? You get if you look at now this again, we have got phi transpose C phi is equal to 2 zeta r omega r, correct. We are writing it in this form, and now we substitute here the damping matrix which we have got, the constant of proportionality was 0.0005 times k phi is equal to 2 zeta r omega r, correct. And therefore, this can be written as 0.005 omega r square into 2 zeta r omega r, correct. So, from here we get a very simple relationship that 0.00 for the rth mode, we can write as 2 zeta r omega r, and therefore zeta r can be written as 0.0005, right, upon 2 into omega r, correct. So, therefore, this is the relationship we got. Therefore, if you substitute now omega r here, we can easily find the modal viscous damping factors. So, therefore, zeta 1 would be equal to how much? You would substitute the natural frequency here, first one, and you would get the result 0.0399, and if you substitute the second natural frequency, you get zeta 2, which is 0.0705. So, this is the solution for the problem, right. So, of course, one more thing I would say here, that alternatively we can also write the phi transpose C phi as a diagonal matrix of viscous damping coefficient, right. So, we can also write in general as phi psi Cr, and now if I substitute in place of C 0.005 Kr, then I can basically write this as phi omega r square is equal to Cr. So, this is an alternative way to reach the same result. So, this gives me 0.005 omega r square is equal to Cr. Now, what is Cr? It is the modal viscous damping coefficient for the rth mode, right. It is the viscous damping coefficient in the rth mode, modal one, right. So, now this gives me Cr, right, and then the damping factor is Cr upon the critical value of the damping coefficient for the rth mode, which actually would be equal to phi omega r square to under root Kr, right. Kr is nothing but omega r square and Mr is 1. So, you can see this essentially leads to the same expression. It leads to the same expression for zeta r as we got earlier, correct. So, you can see in this way we have found a modal viscous damping factor for the two modes. Okay. So, this completes the solution of this problem. Let us go to the problem 6 now. So, this is example number 6. So, let me write the question first. The modal model of an undamped 2 degree of freedom system is given below. Find the displacement, amplitude at the first degree of freedom if a harmonic force of amplitude 20 Newton at 16 Hertz acts at the second DOF, right, and the natural frequencies in Hertz are given as 9.07 and 18.26, and the corresponding mass normalized eigen vectors, right, are given as 0.45, 0.15, minus 0.20 and 0.34, right. So basically model means it's as we studied in lecture classes, model essentially comprises of, for an NDAM case, essentially the specification of the natural frequencies of the mode and the corresponding mass normalized eigenvectors. That specification constitutes basically the model. If it, of course, if it's a damped system, it's a, then the damping factors for different modes also needs to be given. So in this case it's an undamped system, so natural frequencies and mass normalized eigenvectors have been given. Let us look at the solution now. So you can see in this case, we are supposed to identify the response on the structure due to a force acting at some degree of freedom, right, using the information about the model of the system, right. So model typically can be also be identified experimentally, as we are learning in this course through model testing. So if such information is available, then that also can be used to predict the response at different points on the structure, and that is the strength and advantage of the model, right. We do not require the mass and stiffness description of the structure in this case, right. If the model is there, we can use that to find a response on the structure, and this problem is about basically learning that process. So we also studied in the lecture classes that we can find the frequency response function from the model, right. And in the present case, what is the response DOF? The response DOF is given in the problem, find the displacement amplitude at the first DOF. So it means the displacement DOF is the first DOF 1, right. And what is the excitation DOF or the force DOF? That is the force is applied at the second degree of freedom, that is 2. So it means the FRF which is relevant here, which contains the relationship between these two DOFs, is alpha 1 2, right. So therefore the relevant FRF here is alpha 1 2, and alpha means receptance FRF, because we have been asked to find displacement, right. That is why we are considering the receptance FRF. So this is a receptance FRF. Receptance FRFs are based on the displacement response, right. And now what is alpha 1 2? So alpha 1 2, maybe I can go to next page now. So let us write down alpha 1 2, which we studied in the lecture classes. Alpha 1 2 at frequency omega is given by model series expansion, right, with modes varying from 1 to 2, because there are 2 modes in the present case, and then we have phi 1 r into phi 2 r divided by omega r square minus omega square. So this expression we derived in the lecture classes, right, we are using it here. So therefore this we can now expand as phi 1 1 phi 2 1 divided by omega 1 square minus omega square plus phi 1 2 phi 2 2 divided by omega 2 square minus omega square, correct. And then model has been given. So on the right hand side you see all quantities which are appearing, they are basically related to the model, natural frequency and mode shapes. So therefore that we can calculate. So let us calculate the FRF, right, at the frequency. Now here omega is the excitation frequency. So in the present case omega has been given, right, which is 2 pi 16. So so let us substitute the values here. This is 0.45 into 0.15 divided by, now I think we should be careful, the natural frequencies and excitation frequencies are given in hertz, but in this expression the omega 1 and omega, they are basically the radian per second frequencies. So we should always be careful in using the correct value of the frequency. So we should write here 2 pi, and the first natural frequency has been given as 9.07 square minus 2 pi, excitation frequency is given as 16 hertz, 2 pi 16 square, and then phi 1 2, that is minus 0. minus 0.20 into 0.34 divided by, now the second frequency is 18.26 hertz. So, 2 pi into 18.26 square minus 2 pi 16 square, correct. So, this gives us basically the value of the alpha 12 at the excitation frequency, right, at omega, that it is around minus 2.3451 into 10 to the power minus 5, right, meters per Newton. So, this is the frequency response function we have got. So, this essentially says that, this FRF says that if you apply a unit amplitude harmonic force at second degree of freedom, then how much is the response at the first degree of freedom? What is the meaning of alpha 12? Alpha 12 omega is the displacement response amplitude at first degree of freedom if a unit amplitude harmonic force at frequency omega acts at second degree of freedom. That is the meaning of alpha 12, right. And now in our case what we have been asked, we have been given is that the force which is acting at the second degree of freedom, the amplitude of that force is given as 20, right, and that is why if I want to find the amplitude of the response at first degree of freedom, right, omega, right, then this will be actually equal to alpha 12 omega into f2 omega, omega because I am writing because it is at a certain frequency, right, and therefore now we can easily substitute these results here, 2.3451 into 10 to the power minus 5 into 20, correct. So, this gives us x10 at omega, right, at how much we got? We get minus 4.6903 into 10 to the power minus 4 meters, right. This is at 2 pi 16 radian per second. So, this is the result, right. This gives us basically the displacement response amplitude at the first degree of freedom. And now we can see in this problem how from the given model we can predict the we can find the FRF, and also we can use that FRF to find the displacement at any degree of freedom. Okay. So, I think this way we complete the problem solution of problem 6, and now I am going to consider two problems examples which we are going to solve using MATLAB, right. So, now I am going to consider example 7 using MATLAB script, right. So, I am going to first explain the problem and then we will shift to the MATLAB to solve that problem. So, the example is this, let me write the question first. A 3 degree of freedom lumped parameter model described by mass and stiffness matrices is given below. find natural frequencies and mode shapes of the system using a MATLAB script. Also find modal masses and modal stiffnesses, and the M is given as M1, M2, M3, where M1 is equal to 100 kg, M2 is equal to 70 kg, and M3 is equal to 90 kg. And then we have the stiffness matrix, which is given as K1 minus K1 minus K1, K1 plus K2 minus K2 minus K2 and K2 plus K3, where K1 is equal to 2 into 10 raised to the power 8 Newton per meter, K2 is equal to 6 into 10 raised to the power 7 Newton meter, and K3 is equal to 5 into 10 raised to the power 9 Newton meter. So, in this problem, we have been given the mass and stiffness matrices, and then we have been asked to solve the eigenvalue problem. Basically means we have to ask to find natural frequency and mode shapes, which basically means that we have to solve the eigenvalue problem. So, manually already we have learned how to do that in the two examples today at the beginning, right. But here now we are going to write a MATLAB code and then see that how we can use that to solve the eigenvalue problem. Specifically, for example, this is a 3 degree of freedom case, so manual calculation will be even more laborious, and even if the degree of freedom becomes higher, then obviously we will have to fall back on the codes. So, we are going to learn that in this particular example. Then the second example I am going to do is example 8. This also is based on using MATLAB script, right. And now this example is for the system in example 7, it's the same system which has been given in example 7. We need to find and plot the receptance FRF alpha 2 3, right. Maybe I can write it using the convention we wrote earlier, alpha 2 3, right, over 0 to 2000 hertz frequency range, right, using a MATLAB code. So, we have to write a MATLAB code and then do that. Right. The system has proportional viscous damping such that the damping matrix is equal to 0.01 times the mass matrix. So, in this problem the damping matrix has been given as proportional to the mass matrix with a proportionality factor of 0.01, correct. So, now I am going to I have already written the MATLAB codes for these two examples, and now I am going to explain you those codes, and then we will run those codes and see the results. Okay. So, let us shift to the MATLAB software now. Okay, so now you can see this is the code which I have written. You can see the so this initial few statements are required. For example, clear all. What does it do? It essentially clears all the MATLAB workspace. Whatever current variables are there, they are replaced. This is the first statement I have written. CLC essentially means that it clears the command prompt. Everything which is there on the command prompt is cleared, so that when we run the program, all the freshly it will basically display the results, right. That is the purpose of this. Close all essentially closes all the existing figures which are there, right. So when we are running our program, we would like that it does not interfere with the existing figure, so it becomes easier to look at the figure. So that is why these three statements typically help us to very conveniently look at our results. Then now we are defining this is the comment statement, starting with the percentage. It is a comment statement. It is always good practice to have a good number of comment statements, so that when we look at the program, it becomes easier to understand that what those statements are for. So this is we are defining the stiffness matrix first. We are defining the masses M1, M2, M3, and then we are defining the mass matrix M1 0 0 0, M2 0 0 0, M3, right. Then we are defining the stiffness matrix, correct, and then the stiffness parameters K1, K2, K3, and then we are defining the stiffness matrix, right, K1 minus K1 0 minus K1, then K1 plus K2 minus K2 0 minus K2 and K2 plus K3, right. Also you might be knowing that this semicolon at the end of any MATLAB statement, that ensures that the output of when that particular line is executed, the output of that is not displayed at the command prompt. But if you do not have that semicolon, then the output of that statement would be displayed at the command prompt. So this can be used wherever we would like to see the output of any particular statement. Next, now we are solving eigenvalue problem, right. You can see this is the statement to solve eigenvalue, this is the of course comment, and then this is the statement to solve the eigenvalue problem. So EIG is the command in the MATLAB to solve the eigenvalue problem, and it requires two inputs. The first input is the stiffness matrix K, and the second input is the mass matrix M. So these are the two inputs which are required to solve the eigenvalue problem. And on the left hand side you can see the output we get. The first output we get is the eigenvectors, right. These are the eigenvectors, and eval is the eigenvalue. So evac is the eigenvector matrix and eval is the eigenvalue matrix. That is what we get as the output. Okay, and then and you will see generally these eigenvector matrices, they come in the normalized with respect to the mass matrix. So you would see that they are already mass normalized. And now we can find the natural frequencies from the eigenvalues. So this statement, what does it do? On the right hand side, if you see, it takes the diagonal entries of the eigenvalue matrix and then takes the square root of those entries and then stores it in the vector which I have named as NF radian rad sec, which means the natural frequency in radian per second. So this vector is going to contain essentially all the natural frequencies in radian per second. Then next, with the next statement, I am converting these natural frequencies to radian per second. So you can see on the right hand side, I am dividing the natural frequency radian per second vector by 2 pi to get the frequency in hertz. So this basically solves the eigenvalue problem, and we get the eigenvectors and eigenvalues and the natural frequencies. Now to find model masses and model stiffnesses, what we do is that you can see inside, you can see I am multiplying eigenvector, I am taking transpose of that, multiplying it to m, and then multiplying that by again eigenvector phi transpose m phi, right. And then the diagonal, this will be a diagonal matrix, and therefore the entries at the diagonal essentially are the model masses, and that is why I am taking the using the command DIAG, I am extracting the diagonal entries of the diagonal matrix, and on the left hand side then I get MR as the vector of modal masses. And same thing I am doing to the stiffness matrix phi transpose K phi, that gives me the diagonal modal stiffness matrix, and then using DIAG command I am extracting the diagonal entries of the diagonal stiffness matrix model matrix, and therefore storing it in the vector Kr which basically gives me the vector of modal stiffnesses, right. So, this basically completes the MATLAB code. So, once that has been done, you can see I have intentionally not used semicolon at the end of these statements, so that I can see the results of these statements, execution of these statements on the command prompt. So, let us now run this. You can see if I just click here at in the tools commands panel, I say run. Now, you can see it is running and it has completed in fact the run. And if I just stretch it up the command prompt and then I go at the top, you can see first it is giving me the eigenvector matrix, right. And there are, because it is a 3 degree of freedom problem, there are 3 eigenvectors and each column representing one eigenvector, right. Then we get eigenvalues matrix, this is the eigenvalue matrix, it is a diagonal matrix and diagonal values, the eigenvalues are there at the diagonal. So, the first eigenvalue is 0.0314 into 10 raised to the power 7. Then we converted eigenvalues into vector of natural frequencies in radian per second, and these are the natural frequencies radian per second, and the first natural frequency is 560, right, 560.6 radian per second, second is 2321.4 radian per second, and third one is 7498.9 radian per second. Then these are the natural frequencies in hertz, right. So the first natural frequency is 89 hertz, 89.2 hertz, second one is 369.5 hertz, and third one is 1193.5 hertz, correct. Then let me scroll it down. You can see without doing any mass normalization, we get the model masses as unity, which essentially shows that MATLAB is by default normalizing the eigenvectors with respect to the mass matrix, right. So, with MATLAB script then you do not have to explicitly mass normalize them and model masses are unity. And then we get model stiffnesses, which are this, you can see, right, which are essentially the square of the natural frequencies, right. They are the square of the natural frequencies, essentially they are the eigenvalues, okay. So, in this way you can see we have solved eigenvalue problem and found the modal masses and modal stiffnesses. Now, I go to the next example, right, and let me open the file example FRF. So, this is example 8 now. Let me explain you first the code. You can see these are the statements we had in the first problem or exam code as well, right, and then we are defining the mass matrix. So, these are basically identical, this all this part of the code is identical to the first code which I have just copied here. Then after this I am now defining, here the damping is also given. So, now I am defining the viscous damping matrix. Cm is the proportionality constant which is given as 0.01, and then we find the damping matrix C is equal to Cm times the mass matrix, because damping matrix has been given as proportional to the mass matrix. And then now to compute the FRF we need to define the frequency vector. So, you can see now first I am defining the frequency vector so that we can compute FRF at each of those frequencies. So, here I am defining the start frequency. I am want to generate a vector in the MATLAB, we need to define the starting point, end point and the increment. So, f start is the 0 hertz, starts from 0, the end frequency is 2000 hertz as given in the problem, and then we want to compute this FRF with a frequency resolution of 0.5 hertz. So, I have taken DF as 0.5, that is the frequency range, and now we can generate the frequency vector. So, this is the command to generate, or the code to generate the frequency vector. So, it says that start from f start, incremented by df and terminate at f end, and in the process it generates a vector of frequencies, and that vector is named as fvac. Now, we compute the frequency response function. For that, first we define what is the response degree of freedom and the excitation degree of freedom. So, iris I am calling as the response degree of freedom 2, exc I am calling as the excitation degree of freedom as 3, and then Cn is the complex number square root of -1. So I like to always specifically name it with a different variable. In the MATLAB by default the variable notation I, variable I is basically works as a complex number, but just to avoid any conflict with other usage of the variable I in the code, I prefer to define my own complex number like this, Cn as the complex number as square root of -1, so that whenever I have to use it, I use it with full precaution and a caution, right. Then this is the code to compute the FRF over the whole frequency range. So we use a for loop here. This for loop starts from 1 and goes till the length of the f-vec vector. So length f-vec basically gives me the number of elements in the vector f-vec. So this will be around something like I think 4001 most probably, because we are using a frequency resolution of 0.5 hertz. So and then now we compute the excitation frequency 2 pi f-vec I. So it takes the first element in the f-vec vector and computes the radian per second excitation frequency. Then we calculate the dynamic stiffness matrix, which is basically k minus omega square m plus I omega c, which is the dynamic stiffness matrix as we studied in the lecture classes. So this is that we are finding the dynamic stiffness matrix at the current frequency omega, and then the FRF is basically inverse of the dynamic stiffness, right, matrix. So at the current frequency I am finding the full FRF matrix by inverse, so it gives me full FRF matrix. But then because we are interested to only know the FRF alpha 2 3, right, and that is why I am storing only the alpha 2 3 element of the FRF matrix. So you can see on the right hand side I am extracting the 2 3 element of the FRF matrix and storing it in the vector FRF jk, right. Okay. So at each value of the frequency the FRF will be stored. So this basically for loop will compute, it will repeat for all frequencies and it will compute the full FRF for this particular excitation and the force degree of freedom. And next is now we are plotting. So next is because FRF generally we show on a dB plot, so I am converting it to the dB plot, dB FRF. So I am you can see I am taking it as 20 log 10 of the magnitude of the FRF. So FRF jk we computed, then we take the absolute value of it so that we get the magnitude, because FRF will be complex, because damping is there, the FRF will be complex, and then to find magnitude we must take the absolute value of it. In the MATLAB that is the command, and then log 10 and then 20. So that gives me the dB value of the FRF. So again this FRF jk max dB will be a vector, right, of dB values of FRF at different frequencies. And now we are plotting the FRF. So figure, we say that figure, that means it will open a new figure, and then we use the plot command, right, we use the plot command. So in this plot command the first variable is the x-axis variable, which is the frequency vector f-vec, y-axis is basically the FRF magnitude in dB that we have chosen. So this is the minimum we need to have, but of course I wanted to draw it with a thick line, so I have used another command here. I am specifying the line width to draw the plot. I have taken 4, that 4 you can change 2, 3 whatever you wish, and then I wanted a specific color, so I have used the color B. So if you do not give these options, the MATLAB will automatically pick its own options and plot it. So these options are not necessary to be given. And then grid on ensures that the plot has agreed. Then I am saying the label is frequency in hertz on the x-axis, y label is frequency magnitude in dB with respect to the reference value of 1 meter per Newton, and title is FRF 23, right, and then this also is optional. I am setting the font of different labels and the titles to 14. So this completes the program, right. So let us run this program. So let me now hit run here. It is now busy, you can see at the bottom, you can see this is busy in computing the FRF, and now it is plotting. That's we are there now. So you can see the plot is made. On the x-axis we have the frequency, and then on the y-axis we have the FRF magnitude in dB. And since it is a 3 degree of freedom system, we see 3 peaks in the FRF, right. They represent basically the FRF the response the frequency response going up becomes very high when the excitation frequency matches the resonance frequency. Again, when the excitation frequency gets offset with the resonance frequency, the response comes down. So you can see it has 3 resonance peaks, and there is also an anti-resonance here. At the bottom you can see at this frequency somewhere around it looks like something like 180 or 190 hertz, there is an anti-resonance frequency, right. So this is how we can plot the FRF. So I think in this way we have solved this MATLAB based examples also, and then we have seen the results, right. So in this way we come to the end of this session, right. We solved around 8 problems, right. Now we can stop here. Dhanyavad. Thank you.